Hey, it's Plumber Tom. Don't forget to check in the comments below for a link where you can find additional resources like practice tests and courses that you can take. Your support helps me to be able to create more great content. Thanks for watching. Hello, welcome to this presentation where I am going to introduce you to the very basics of hydronic heat. Now, this is intended as an introduction to the International Mechanical Code, Chapter 12, which is all about hydronic piping. But if you're going to study that, you kind of need to know how these systems work. And the truth is, a lot of plumbers don't end up spending much time on hydronic heat. That's fine. You can be a plumber, have a successful career, and never touch a hydronic system. But at the same time, hydronic systems are all about pipes, and plumbers are all about pipes. So if you're a plumber and hardly ever touch hydronic, that's all right. This is going to be informative, and you'll be a more educated plumber after you watch this. And then, if things ever slow down or you want to expand your business, you can always do hydronics. So let's go over some of the basics of hydronic heating. Now, I am a plumber and I speak primarily to plumbers, but the fact is that hydronic heat is often installed by HVAC contractors as well. It can go either way, right? This is really this crossover area where plumbers can do full hydronic radiant systems. Sure, we pipe those all the time. But again, an HVAC contractor may decide to branch into that because it's about heating and that's what they do. And that's okay too, as long as we all know what we're doing. In this presentation, we're going to look over some of the basic components that make up these hydronic systems, starting with the heat source. You're going to have a boiler or some way to heat up the water. Then you're going to have some way to move the water. So you'll have circulation pumps. There'll be piping that will be able to transfer that fluid around and distribute the BTUs, and radiators or in-floor tubing or some way to further bring those BTUs into the space and heat the space. In order for these systems to work properly, we're going to have different maintenance equipment, and we probably need to add water occasionally, so there'll be a make-up water connection. Finally, there's going to be electronic system controls, and that's what's going to give us power over the whole thing. And it gives us the ability to create customized temperature zones where some areas may be heated more than others. That's nice. We'll look at each of these parts of the hydronic system, but let's start out with something really basic. Here we have a diagram with a single loop, very simple stuff, and I'm not even indicating all of the possible controls and things that could be on here. But let's just keep this simple. There's a boiler. That's our heat source. There's a loop. It's sending that hot water out, and it's coming back. We're going to have a pump and a place where that water is radiated out into the space. In addition to that, it's good to have an expansion tank, an air separator, and on this one we also have a drain valve. This is pretty basic, right? But in the early days of hydronics, it was really basic, just like this. We'd push the water around through some baseboard radiators, and it would take care of our needs. Here's another similar diagram from Nordic. They have boilers and other controls. But it's basically the same thing, right? We have the boiler, a loop going around. You can see the air separator, expansion tank. There's a pump and a manifold system that's going to send that hot water out to the different zones, recollect that, and bring it back to the boiler for reheating. Examine this diagram. We've expanded it a little bit. Rather than having a single loop, that loop branches into multiple areas where we're trying to heat. But ultimately, we're still a pretty simple system. We have a single pump that's pushing through both radiators, and that water is being sent out and brought back to the boiler. Now, another thing we've added to this diagram is the water that would feed this system. That's going to be our makeup water, and we'll talk about that a little bit later. Let's step through each of those important components of a radiant system, and then we'll have a look at the whole thing again. Now, of course, we start with the boiler. That's what's going to heat the water, but there's a lot of different sizes and options for that. Residential boilers, such as this Navian, can be hung on the wall. They don't take up a lot of space, but they're capable of heating the entire building. Commercial boilers are far larger. They're installed in large mechanical rooms. Often there's multiple of them, and they are capable of heating an enormous amount of water. Next, we have the circulation pumps. Of course, once we've heated the water, we need to push that around. A lot of times on a plan, a circulation pump is indicated by a circle with a triangle, and these are directional. The triangle is going to point in the direction that the water is going to go. This symbol on the diagram is a check valve. It indicates that the water can only move in one direction and it will not be allowed to move in the opposite direction. A simple system may only have one pump, like the single loop we looked at the beginning. But more complex systems may have many pumps. Like these residential pumps that are all piped in a series together. The water is heated from the boiler, and each of those pumps can move that water into individual zones. On a commercial system, we see a similar thing, only these pumps are very large and often mounted on the floor. Then we come to the distribution piping. As we study the International Mechanical Code, we'll talk about all kinds of pipes that can be used, but they all serve the same fundamental purpose, which is to distribute that hot water out to where it needs to go. That includes supply pipes, return pipes. These pipes often pass through manifolds with flow controls and are distributed out into zones. A manifold is basically just a series of valves built together. You can build a manifold if you want. A manifold like this is a series of copper T's that have been installed and soldered together, but it is a manifold. But it's way easier to just buy a set. Manifolds often come as a set so that they can accommodate the zones. The tubing can be connected to one side, go out through the building, come back, connect to the other, and be sent back to the boiler. Manifolds can also be used to control the different circuits. Here's the fact. Water is lazy. It will always take the shortest route through anything. So, if one of the loops is longer than the other loops, well, the water is always going to pass through the shorter loop, and it won't go through and heat the one that's longer. So how do we compensate for that? Well, you can use a manifold with circuit setters that you can create resistance on the shorter loops. Or rather, you're closing it down a little bit until it equals the resistance of the tubing on the long loop. This is called balancing as we go through each of the zones and make sure that when water is being pushed out, it will move equally through all of them regardless of their length. And a circuit setter manifold is going to allow you to do that. These sort of manifolds should be installed in a location where you can get to them and be able to adjust those controls, because over time, systems will come out of balance and they need to be recalibrated. Once the water has passed through that piping and through the manifold out to where it needs to go, there has to be a way to transfer those BTUs into the space. For many years, this was accomplished by baseboard radiators, and they still work great. Those radiators need to be sized for the space that they're in so that they can apply enough BTUs. But basically, they sit at the floor, the pipe comes in, the pipe goes out, and the heat's distributed through that radiator. In-floor heat is a far more comfortable form of hydronic heat because your entire space is being heated from the floor up, instead of just a radiator by a window. This also aids in recovery. For example, if I have a room with in-floor heat and the tubing in the floor is heating the air in the room, when I open a door to the outside and cold air rushes in and the warm air rushes out, once I've closed the door, that room will immediately begin to heat from the floor up, and it can recover very quickly because the whole room is the heater. This is why it's comfortable and why it's popular. While there are a lot of different pipes that can be used in hydronics, when it comes to radiant, most of the time people are using PEX, which should be an oxygen barrier PEX. That means it won't allow gases to pass through the permeable wall of that plastic tubing. That's not a big deal if you're dealing with potable water and you're constantly moving water through the pipes to plumbing fixtures. But when you're circulating that in a closed loop, oxygen getting through the PEX walls, which crazy as that sounds, it happens. It can get in there and that oxygen will go and eat up the parts in the system. That means the valves, the pumps, the boiler itself. Oxygen barrier PEX is important to use. When it comes to the piping of a hydronic system, it's important to have a good plan as to how to bring that all together. If not, it's going to be a chaotic mess. So you want to make sure to have a good layout as to where things are going to go and how they're going to connect. A manifold can be really helpful in this because it already lays things out in a series.
I got my boiler and my pumps. My work is the best.
Put it all together, and I never guess.
Cause when I do mechanical, I build with a plan. My work is always awesome. Cause I am the man.
Oh yeah. Oh yeah. Mechanical me. Oh yeah. Mechanical me. Oh yeah. You gotta see. Oh yeah. Mechanical me. That brings us to the installation of the tubing in the floor itself. This has been evolving for decades. And unfortunately, there are a lot of poorly installed systems over the years. It's kind of been experimental. And for that reason, some hydronic systems have kind of given a bad name to the rest of it. If installers don't know what they're doing, or even earlier on, if the systems just weren't designed well or very efficient, yeah, they're going to be less effective and expensive to run. Let's look at a few different ways that tubing is installed for the use of in-floor heat. A lot of times it is installed with the intent to be poured below a cement floor. This can be done in big commercial settings, workshops, large buildings, or it can be done in smaller scale residential buildings in those frame walls of the building. The overall principle is basically get those tubes out there and coil them back and forth, run them in a way that they're going to span certain spaces or create zones, and bring them all back to a central location where they can be connected to a manifold. Manufacturers do have specific recommendations as to the spacing of the tubing and the size of the tubing and things like that. Often, in-floor heat is poured into a concrete floor. This can be even done in a framed wood building using a thin, liquid-like concrete called gypcrete. It's like cement without any rocks, and it flows really easily. It's lighter weight, and it can sit in a thin layer right over the tubing. So this has been done for many years in residential. But you can imagine how fun it is to pour cement all over on the inside of a framed building. I mean, I'll tell you, there's really no easy way to do this. It's going to take a lot of work and a mess. So some manufacturers have created ways to connect that tubing on the underside of the floor. That way you don't have to pour cement over all the floor. That does get kind of expensive if you think about material costs. The problem is if you're trying to heat the floor above, and it has to radiate through the subfloor, the carpet pad, and the carpet itself. Those are all insulators, and it takes a lot more energy to get that heat up into the floor. And at the same time, please recognize radiant heat goes in all directions. So while you're trying to force BTUs up into the upper floor, you're also pushing BTUs down into the floor below, and it can overheat the space underneath that floor. So manufacturers have come up with ways to try and minimize that problem by adding different insulation layers on the underside and try and get as much of that heat to go up as possible. In this case, rather than pouring cement over the top, they've channeled the plywood, cut little grooves so the tubing can move through that. Other manufacturers are creating recessed panels like this where the tubing can sit right down in there and it can be built into the subfloor. And there's also a movement among manufacturers to create a big mat that makes it very easy for laying out the tubing. The tubing sits nicely down inside the mat. Now this would be intended to have cement poured over the top of it, but it creates for a very consistent installation. Ultimately, I think that these methods are possibly going to continue to evolve as people try and solve this problem of how do you get that radiant into the floor without losing BTUs in places you don't want it to go, and minimize installation costs because it does take a lot of work to roll all this out and get it set where it needs to go.
Oh yeah. Oh yeah. Mechanical me. Oh yeah. Mechanical me. Oh yeah. You gotta see. Oh yeah. Mechanical me.
There is a lot more that could be said about piping on a hydronic system, but let's move on to system maintenance, different components that are added to these systems to make sure that they operate safely and properly over time, starting with the expansion tank. Anytime we're heating water, that water is going to expand, and especially on a closed system like hydronic systems are, where everything's sealed up in a loop and we're just moving hydronic fluid around, we need to have a place for that water to expand as it heats up. So, of course, we're going to install an expansion tank. Expansion tanks come in different sizes, from little ones that we would typically install with a potable water heater to ones that are enormous for big hydronic systems and would need to be mounted on the floor. It's important on every system to have a way to purge or drain the system. So having hose bibs or little drain valve faucets is a really good idea on low points or on the boiler to be able to drain out that system as needed. Another issue with hydronic systems is that if there is air in the system, it will not flow. It will create an airlock and can even burn up a pump. So each system should have some way to remove the air These are called air separators. And again, they come in all sizes, but you'll find these at high points in the system. And of course, we'd want to monitor both the temperature and the pressure of the system. So having gauges and thermometers at strategic locations is going to help us to see and diagnose how the system is doing. It's helpful when installing a gauge to also have a shutoff valve there so that you can easily change that gauge without having to drain the entire system. Hydronic systems mostly consist of water. It's smart to add chemicals that will help the system to last longer and preserve the components of the system. But in any case, there are times when we'll need to refill the system. Maybe there was a leak, or maybe we had to drain it down for maintenance purposes. So having a makeup water or a connection to potable water is really helpful, because then we can just push the water in. However, we of course want to protect our potable water because we don't want any of those chemicals to get back into the potable system. So makeup water is often going to have a backflow preventer, a pressure reducing valve, because often these hydronic systems operate at far lower pressures than we have on the potable water system. And if there's a chemical feeder, that would connect downstream from the backflow preventer. And then of course we have the electronic system controls. These are connected to thermostats, which will read the temperature in the space and tell the system when to run. Running basically means boiler is firing and pump is turning, and that's going to move that hot water out to the space. When the thermostat reaches its set point, it will tell the system that's enough. It will shut off the pump, and if hot water is not needed in other parts of the system, then the boiler can shut down as well. Now that we've discussed a lot of different components that make up a hydronic system, let's have a look at this diagram. Notice that there is a boiler that's going to create the heat and a primary loop, one loop that's going out and coming back to the boiler. Then branching off, we have additional loops, secondary loops that are sending hot water from that loop out into the heated space and bringing them back. Notice that on this diagram, we have more pumps, a pump for the primary loop and pumps for the secondary loop. Now, anytime we start to create more division like this, we have more control. We can heat this space or that space to different temperatures. But of course, we also need to implement more valves and more system controls. And so the system becomes a little more complex. Overall, if you're trying to create the most comfortable heating experience, the more of this that you can add with individual zones for certain areas is the better way to go. And this concludes this basic explanation of hydronic heating. Have I covered everything? No way. But hopefully this helps you understand a little more of what goes into a hydronic system. As we study the International Mechanical Code, we'll be looking at code requirements talking about specific parts of this system. So it's helpful to understand these different parts that make up a hydronic system. I hope you find this explanation helpful as we move into International Mechanical Code, Chapter 12, Hydronic Piping. I'll see you in the next one.
Oh yeah. Oh yeah, mechanical me. Oh yeah, mechanical me. Oh yeah, you gotta see. Oh yeah, mechanical me.